A pre-tensioned beam (250 mm) wide and 300 mm deep is pre-stressed by 12 wires of each 7 mm diameter initially stressed to 1200 Newton per mm square with the centroids located at 100 mm from the soffit. Estimate the final percentage loss of stress due to elastic deformation, shrinkage, creep, and relaxation using IS 1343/2012. So along with this one, certain data is also given. Relaxation of steel stress is equal to 90 Newton per mm square. Creep coefficient is equal to 1.6. Residual shrinkage strain (3 into 10⁻⁻⁴). Modulus of elasticity of steel ES is equal to 210 kilonewton per mm square. Modulus of elasticity of concrete EC is equal to 35 kilonewton per mm square. So this is the question, and with this given data, we need to calculate what are the final percentage losses of stress due to elastic deformation, shrinkage, creep, and relaxation. If you are having any difficulty in understanding my writing, let me know. If any point is not clear, Okay, so why I'm waiting is you people have to write along with me. That's why I'm waiting. Just see, understand the question. It is a pre-tension beam 250 mm wide and 300 mm deep is pre-stressed by 12 wires of each 7 mm diameter. Now, initially stressed to 1200 Newton per mm square with their centroids located at 100 mm from the soffit of the beam. That is given. So they are asking us to estimate the total losses. So here the relaxation of steel stress 90 Newton per mm square is given. Creep coefficient is given 1.6. Residual shrinkage strain is given 3 into 10 power minus 4. Then modulus of elasticity of steel as well as modulus of elasticity of concrete are given. So we'll write down the given data. So with this given data, do we require anything? We'll see. So first of all, given data. In that, first of all, draw the beam that is given to us. So what are the dimensions that are given here? 250 mm wide and 300 mm deep. So this will be our neutral axis. And it is given that the width is 250 mm. And the depth here it is 300 mm. So here the level of prestressing steel is somewhere here, and it is mentioned that the centroid of all the CGs from the soffit. Soffit is nothing but bottom. So just once again, soffit is nothing but bottom. So from the bottom, it is from the soffit of the beam means here it is 100 mm that is given in the question. So you can calculate from here to here. This is 150 mm. So if this is 150, so obviously the eccentricity from the neutral axis, it will be 50 mm. So E is equal to 50 mm that we can calculate. So write down the given data here. B is equal to width of the beam. B is equal to 250 mm. Depth of the beam is equal to 300 mm. Eccentricity E is equal to 50 mm. Eccentricity E is equal to 50 mm. Now, it is said that the wires are 12 in number and each having 7 mm diameter. So, the diameter of the wires as given 7 mm, we can calculate APS, area of pre-stressing steel. APS is equal to 12 in number, so 12 into pi by 4 into 7 square. So what is this value? Square. 461.81 mm square, that is the area of pre-stressing steel. Initial pre-stress value is already given, which is 1200 Newton per mm square. That's already there. So we can calculate what is the pre-stressing force, initial pre-stressing force. So we can calculate what is the area of cross section, that is B into D, 250 into 300, which is 75 into 10 cube mm square, as well as moment of inertia, PD cube by 12, 250 into 300 cube by 12 mm power 4. ES is equal to 210 into 10 cube Newton per mm square, as well as modulus elasticity of concrete 35 into 10 cube Newton per mm square. So M is equal to ES by EC. So 210 into 10 cube by 35 into 10 cube, the value is 6. So modular ratio M is equal to ES by EC, which is equal to 6. So now we need to first of all calculate the loss of stress in steel due to elastic deformation. So one by one we will calculate the losses. So first loss. Due to elastic deformation. So here the value is nothing but due to this, the loss of pre-stress in steel due to elastic deformation is equal to M into Fc. So we need to recall our formula that we derived previously. So this is equal to M into Fc. So M is already known, which is 6, whereas Fc is to be calculated. So Fc is nothing but stress in concrete at level of steel. So Fc is equal to, so we know that P by A plus P into E squared by I. So you are calculating the stress in concrete at level of steel. So this is your cross section. So this is your neutral axis. The steel is at this one. So at this level, the stress in concrete is to be calculated, which is Y will become here E. So that's why P by A plus P into E into Y by I, that Y will become E. Now P is already known, which is already obtained in the above one, 554.2. So 554.2 into 10 cube by area of the cross section. So area of the cross section is calculated as 75 into 10 cube plus 554.2 into 10 cube into eccentricity is 50 mm. By moment of inertia is 562.5 into 10 power 6. The value is plus 9.85 Newton per mm square. So this is loss of stress in steel due to elastic deformation is to be calculated. So which is loss due to elastic deformation is equal to plus that is, wait a second. So loss of stress due to elastic deformation is equal to M into Fc. M value is 6 here. So 6 into 9.85. Please bear with me. Today, like the ESET admissions were going on. I had to cancel the class, but rather than canceling the class, I would like to take the class. Okay. So have you completed this? What is that value? Is it okay? Loss of stress is calculated. Now we have to calculate, yes, next step. Loss of stress in steel due to shrinkage in concrete. So loss of stress due to elastic deformation is calculated. In the second step, we'll calculate loss of stress due to shrinkage. Due to shrinkage, that is to be calculated. So in this, so what is the formula that we are going to see? So the loss of stress due to shrinkage is equal to epsilon Cs into Es. So stress is nothing but shrinkage strain multiplied with the modulus of elasticity of steel. So in this shrinkage strain, just if you go to that question, it's already stated that the residual shrinkage strain is given as 3 into 10 power minus 4. So right now we need not calculate. Just check it whether the screen is visible or not. So residual shrinkage strain 3 into 10 power minus 4, that is already given in the question. So we can directly substitute that value here. So epsilon CS is equal to 3 into 10 power minus 4. Now ES is already known, that is 210 into 10 power 3 Newton per mm square. So loss of stress directly we can calculate it. Here we need not calculate using our order provisions, as that is directly given in the problem. So 3 into 10 power minus 4 into 210 into 10 cube. So which is 63 Newton per mm square. The loss of stress due to shrinkage.
Sir, screen is not visible, sir.
It's visible. Just in front of my name, just please pin it. You might have pinned someone. Just unpin it once. It's visible, right?
Yes, sir.
So loss of stress due to shrinkage is 63 Newton per mm. The next one is loss of stress due to creep. So loss of stress in steel due to creep in concrete. So here, to calculate this, we already know that there are two methods that are available: ultimate creep strain method, and another one is creep coefficient method. So just go to that which method we have to follow. So here, according to the given data, we can understand which method we need to follow. If ultimate creep strain is given, then we need to go with the creep strain method. But here, creep coefficient is given. So as creep coefficient is given, we'll go with the creep coefficient method. So here, epsilon cc into fc into es, that is already creep ultimate creep strain method. The formula loss of stress due to ultimate creep strain is this one, whereas the loss of stress due according to creep coefficient method for creep is phi into m into fc. So this is as per creep coefficient method. So this phi is nothing but related to the creep coefficient. So this is phi. So phi into m is modular ratio. Fc is nothing but stress in concrete at level of steel. So phi into m into fc, that I can substitute directly here. That means according to the given creep coefficient, we will decide whether we should go with the creep coefficient method or ultimate creep strain method. So this is phi into m into fc. So whereas phi is equal to 1.6, which is given, m is modular ratio is 6, fc. Fc is nothing but just in the previous step we calculated stress in concrete at level of steel, which is plus 9.85. So this will be substituted as plus 9.85 Newton per mm square. So loss of stress in steel due to creep in concrete. The loss of stress in steel due to creep in concrete is 94.56 Newton per mm square. The next loss is loss due to relaxation. Loss due to relaxation of stress in steel. So just go to the top. If it is given in the data, it may be given either 5% or 3%, or otherwise the value will be directly given. Just see this one. Relaxation of steel stress is 90 Newton per mm square. So if this 90 Newton per mm square is directly given, we can consider this as this is the loss. So that is directly given. So take that value, which is 90 Newton per mm square. So substitute that one here. So the loss of stress due to relaxation of stress in steel is 90 Newton per mm square. So total losses is equal to, so here this is the loss that is happening in pre-tension concrete beams. So add everything: loss due to elastic deformation, plus loss due to shrinkage, plus loss due to creep, and finally loss due to relaxation of stress in steel. So all these losses, they are happening in pre-stressing steel. So this will be loss due to elastic deformation. The value is already obtained in the first one, which is 59.1. So this is 59.1. Due to shrinkage is 63. Due to creep is 94.56. And due to relaxation is 90. So the value of these total losses are, 306.66 newtons per mm square. Now we need to calculate percentage losses. So to calculate this percentage losses, so that is loss by initial stress into 100. Loss is 306.66 by initial stress is 1200 into 100. That is a value. So this is how we will calculate the total losses. Now just see this one. If the losses are 25.5, efficiency eta is equal to 100% minus 25.5. Just you can check it as 74.5%. The efficiency of this one is nothing but 74.5%. So 100% minus losses, that will give you the efficiency. The previous problem we did with pre-tensioned beam. Now we are doing with post-tensioned beam. 250 by 400 mm deep is pre-stressed by 12 wires of 7 mm diameter, initially stressed to 1200 Newton per mm square. The cable profile is parabolic. With zero eccentricity at supports, and 120 mm at the center. The span of the beam is 10 meters. Estimate the loss of pre-stress. Due to various factors. and the percentage loss from the following data. Yeah, good morning. Just inform in the WhatsApp group, ma. Inform in the WhatsApp group. You say that I am the detained candidate. Yeah, you have informed. No. Just in the group itself, you can say. If you call me, then what I can do right now? I am in the class. The percentage loss for the following data. Grade of concrete. M40. Yes. 210 kilonewton per mm square. Shrinkage strain. 3 into 10 power minus 4. Relaxation of stress in steel is 4%. Creep coefficient 1.6. Creep coefficient 1.6. Coefficient of friction between cable and duct is 0.55. Wave effect 0.0015 per meter length. Anchorage slip 3 mm. EC is 5000 FCK. So just this is the given data. With this given data, we need to calculate the losses of pre-stress due to various factors. So we know that a post-tension beam will be subjected to 6 types of losses. And first loss is loss due to elastic deformation. Second one is loss due to shrinkage of concrete. Loss due to creep of concrete is the third one. Loss due to relaxation of stress in steel is the fourth one. Loss due to friction. And the last one is loss due to anchorage slip. So total 6 losses are there. So these are the factors that will affect the pre-stress that is applied, and we need to calculate the loss of pre-stress due to these factors. And you can observe here a parabolic cable is given. So with this parabolic cable, and you can observe that 0 eccentricity at the supports and 120 mm at the center. So with this, now we'll calculate, first of all, write down the given data. So you can observe here with the this is our cross section of the beam, and this is the length. So this is the neutral axis. So you can see that at supports it is 0, at center this is 120 mm, like this. So at center span, the eccentricity E is equal to 120 mm. Eccentricity E is given as 120 mm. So now you can observe here, this is 120, here this is there. So this precision force here, this is 120 mm. Now, the length width is given as 250 mm. So note down this as 250 mm, and this depth is given as 400 mm. Now, just given data, write out the given data. B is equal to 250 mm. D is equal to 400 mm. E at supports, it is eccentricity at supports is equal to 0. E at the center span 120 mm. And the span of the beam is given. L is equal to 10 meters. Just let me check whether we have written the span of the beam or not. Yes, we have written the span of the beam is 10 meters. So span is 10 meters. Span is 10 meters. Now just check it. If I know the span of the beam, what is the slope here that is made here? What is the slope that is made here? So the tangent at this one, the slope we can calculate it. It will be written as 4E by L. Just you can remember, or otherwise that is 4E by L. So slope theta at this one is 4E by L. So this is E and L is nothing but 10 meters. So 4 into 120 by L is 10 meters. So in terms of convert in terms of mm, so you will get it as theta. In terms of radians, you will get it. Area of pre-stressing steel, APS is equal to, it is given that there are 12 number of bars are there, and these 12 wires, each of 7 mm diameter, they are there. So this is 12.81 mm square. So initial pre-stressing force is already given, which is 1200 Newton per mm square, and the pre-stressing force P is equal to APS into FPI, 461.81 into 1200. That is the pre-stressing force. So you can calculate what is the area of the cross section, which is B into D, which is 250 into 400, which is 10 power 4 mm square. And moment of inertia is BD cubed by 12, which is 250 into 400 cube by 12. Now we can calculate the stressing concrete at level of steel is to be calculated. So before that, first of all, we'll calculate what is the modular ratio. So modular ratio M is equal to ES by EC. So here to get this EC, EC is given as 5000 root FCK. So this is 5000 root FCK value is, what is the grade of concrete taken? 40. So modular ratio M is equal to ES is 210 into 10 cube Newton per mm square by 31.62 into 10 cube. You will get the value ratio M is equal to 6.64. Now see this, your beam is eccentric at center span and it is concentric at the supports. So when you calculate this FC, that is stress in concrete at level of steel, we need to calculate the average value as it is not constant throughout the span of the beam. So stress in concrete at supports, FC support is equal to, so here P by A plus PE square by I, where your eccentricity E is, this term will become 0 as eccentricity is 0, only you will take it as P by A only. So P is nothing but prestressing force 554.17 into 10 cube newtons by 10 power 4. So that will give you the stress in concrete at supports.
.54.
Plus 5.54 to Newton per mm square. Now, stress in concrete at center span. So, its mid span is equal to P by A plus PE square by I. So, this is 554.17 into 10 cube by 10 power 4 plus 554.17 into 10 cube into 120 square by moment of inertia 1.9. What is the moment of inertia? That is up to 1.33. So this will be written as 1.33 into 10 power 9. So here FC at midspan will be calculated as 0.54 Newton per mm square. So we need to calculate average value. We should remember when a parabolic tendons or when a parabolic cables are given, so we should consider the average value. FC average is nothing but FC supports plus 2/3 of FC midspan minus FC support. So this is FC supports is plus 5.542 plus 2/3 of 11.54 minus 5.542. So this is FC average will be calculated. So stress in concrete FC average is calculated. Now we will calculate it.
At the supports 55.417, sir. It is 55.42.
55.42.
It supports
51.55.4.
417. 8 10 into 10 power 4, sir.
10 into 10 power 4 already. No, area, is there any mistake in the area?
Yes,
So
sir.
is it 10 power 5? Just make a correction for this one. This is 10 power 5 mm square. So this is 10 power 5 mm square means, so area is 10 power 5 mm square. If you substitute this value here, so this will also be corrected as 10 power 5. So then the answer will be plus 5.54 to Newton per mm square. Just make a correction of this one. This is 10 power 5. So plus 5.54 to Newton per mm square. Now the values are convinced. So this is also 10 power 5 only. So FC average is 9.54 Newton per mm square. Is it right now?
Yes, sir.
Right. So FC average is calculated. Now we will calculate first one. Loss of pre-stress in steel due to elastic deformation. So due to elastic deformation. So regarding this elastic deformation, once see this one. We remember when post-tensioning is considered, when all the wires are stretched at a time, when all the wires are stretched at a time, then there is no loss. When one of the wire is stretched and the next wire is stretched and locked, then the loss of pre-stress occurs. Now in this, the loss of pre-stress in steel due to elastic deformation, it is not mentioned whether all the wires are stretched or the wires are stretched one by one. It is said that there are 7 wires, 12 wires are there of 7 mm diameter, but the data is not given regarding the sequence of stretching and anchoring. So stressing and anchoring, whether they are done all at a time, then the loss due to elastic deformation is 0. So write down, assuming the wires are stressed and anchored at a time, then loss of pre-stress due to elastic deformation is equal to 0. So here we are assuming that all the wires are stressed and anchored at a time, when the loss of pre-stress due to elastic deformation is 0. That loss is completed. Now second one, loss of pre-stress due to shrinkage. So we know that the loss of pre-stress due to shrinkage is equal to epsilon Cs into Es. So epsilon Cs value, if you observe, is it given in the question or not? Just check it. Check the question. So epsilon Cs shrinkage strain is 3 into 10 power 4 minus 4. 3 into 10 power minus 4, that is given. So we can directly take that. So this is 3 into 10 power minus 4 into Es value is 210 into 10 cube Newton per mm square, which gives you 63 Newton per mm square. This is the loss of stress due to shrinkage in concrete. So first loss is 0, second one is 63 Newton per mm square. Then the third one, loss of pre-stress due to creep in concrete. So we have already seen that in the question, creep coefficient is given as 1.6. Just see the question. So the creep coefficient is already given. So loss of pre-stress due to creep is equal to 5 into m into Fc. That's it. The loss of pre-stress due to creep is equal to 5 into m into Fc. So the creep coefficient is 5 is 1.6. And modular ratio m, just we calculated it as modular ratio value 6.64. So modular ratio is 6.64 into Fc. That is Fc average you need to consider, which is 9.54. So that will give you the loss of pre-stress due to creep in concrete. Fourth one is loss of pre-stress due to relaxation. So just you can see that the relaxation loss is equal to, it is given in the question, the relaxation of stress in steel. Just make a correction of it. Relaxation of stress in steel is equal to 4% of initial stress. So initial stress, it is given in the question as 1200 Newton per mm square. So with this, that will give you the relaxation of stress in steel, which is loss of pre-stress due to relaxation, that is 48 Newton per mm square. So loss of pre-stress due to relaxation is 48 Newton per mm square. Loss due to friction, so this is the formula. The loss of pre-stress due to friction is equal to P naught into Kx plus mu alpha. So you can consider this as, this is initial stress. So P naught is considered as initial stress. Just I am running out of time, that's why I am slightly moving fast. So P naught is initial stress, which is 1200 Newton per mm square. We used to write it as FPI. And K is nothing but, it is given in the question as wave effect, which is 0.0015 per meter length. Per meter length. So just you can refer your question, wave effect coefficient K is given and X is nothing but L here, 10 meters per meter length. So for the entire length of the span 10 meters, X will be considered as 10 meters. So here X will become L by 2 when the stretching will be done on both the sides. So if this is your tendon's position, if the stretching is done on both the sides, then X will become L by 2. Why? Because from here to here, this span it is L by 2 and this span will be L by 2. Here, if the stretching is done only from one side, that means here it is anchored and the stretching will be done only from one side, then that will be considered as X is equal to 10 meters. Then here, mu, the coefficient of friction between cable and duct is given as 0.55. And alpha will be considered as, here this is, alpha will be considered here like this, which is 2 theta. Alpha is cumulative angle of rotation. Cumulative angle of rotation, which is 2 theta. That is 2 into theta is already calculated in the previous step, 4E by L, which is in terms of radians, 0.048, that is equal to 0.096. So alpha is 0.096 radians. So we know all these values, so you can calculate this loss of pre-stress due to friction, that is nothing but 1200 into K is 0.0015 into X is 10 plus mu is nothing but 0.55 into alpha 0.096. So that is loss of pre-stress due to friction is calculated. Loss of pre-stress due to anchorage slip. So here in the question, delta is given as 3 mm and the loss of pre-stress is nothing but pre-stress. The loss of pre-stress is equal to delta into ES by L. So how we have derived this one? We know that delta is equal to PL by AE, and this is P by A is nothing but stress. So stress is nothing but delta into ES by L. So that is how we got this formula. And this is delta is 3 mm, ES is 210 into 10 cube, and length is 10 into 10 cube. Convert the units in mm. Make a consistency of the units. So this will give you 63 Newton per mm square. So add everything, you will get the total loss. So total loss is equal to, add all the losses and you will get the total loss, and that value, with that value we can calculate a percentage loss, and that percentage loss will be calculated like this.